So once we launch a satellite into space, simply lifting it up isn't enough. To actually keep it in orbit, we must give it a very specific sideways speed, that is your horizontal speed. This required speed is your orbital velocity. So orbital velocity is a minimum horizontal velocity an object must maintain while revolving around a planet so that it does not fall due to gravity. So official definition is orbital velocity is the precise horizontal speed an object must have at a given altitude to maintain a stable closed trajectory, a circular or elliptical orbit around a central massive body where the gravitational force is exactly balanced by the required centripetal force. So mathematically, it would turn out to be this. H is the height, basically R is your radius of the planet. Anyways, we'll be talking about this now. So I have a satellite. I want it to go round and round in this manner. So what is that velocity with which we should throw so that this happens? So that's the question. So we have something like this. No, that is too much. Okay, so that's better. So basically we are looking at not that. Yeah. We are looking at this tangential velocity, say v naught. And this is at a height of, this is moving at a height of h. And this is going in a circular orbit around a planet whose radius is r, mass is m, I think, and the mass of this satellite is small m. So these are all the things that we need. Now we'll start with our statements. So first thing is we'll talk about let m be the mass of the planet, m be the mass of the satellite, r be the radius of the planet, h the height at which, this I think I'll describe, h height of the satellite, above the planet's surface. Then r plus h will be the orbital radius. Of the satellite. Okay. Right, yes. Now, very first thing is what we know is, as per the law of gravity, we have the force that is needed to keep the object the force with which the object is pulled on, my bad. The force with which the satellite in this case is pulled on is this. Why is this important? This will be the centripetal force that will keep it going round and round. So centripetal force, I hope you guys remember, it is to do with your circular motion and everything. The centripetal force required by the satellite to keep it in its orbit is given by m into AC. This is m times of AC is v naught square by r plus h. So under the equilibrium scenario, these two values will be equal. Under the equilibrium condition, centripetal force is provided by gravitational pull. Right, guys? So mv naught square divided by r plus h. So that's how we'll get an expression for v naught. That's it. So gmm by r plus h the whole square. So this and this will get cancelled. This and this will get cancelled. So v naught square is gm by r plus h root. Okay, next we will substitute g by g is equal to or gr square, or actually it should be the other way around, gm as g r square. So where we have our g to be your, where, what is g? Acceleration due to gravity near the Earth's surface, due to gravity near the planet's surface. So we have v naught also equal to gr square by r plus h root. I think we have the final expressions. Yeah, that's it. So clearly the v naught, this velocity is independent of the mass of the satellite, that is. The velocity decreases with the increase in the radius of the orbit. Clearly depends on the mass and radius of the planet as well, about which the satellite revolves. Clearly. So that's your orbital velocity.